Okay, so we would like to discuss the properties of the Q-binomial coefficients. And those properties are going to be in analogy to the properties of the classical binomial coefficient. So first of all, let's recall the properties of this coefficient. So we have a situation where we consider m plus k over m. And this is precisely a sum over all Young diagrams that are contained in the grid with m rows and k columns. And we take the powers of q raised to how many are the, or to the length of the partition that we're considering, which means what number we're actually partitioning. So let's recall what this looks like. So for example, this is the case where m is 2 and k is 4. And a Young diagram will look like something like this. So in this case, of course, lambda consists of the numbers 4, 2, and it partitions the number 6. So the length of this partition is 6. Also, it's important to remember that any such diagram is associated with a path from the lower left corner to the upper right corner that consists of exactly m plus k steps. So in our case, that would be 6 steps. And the choice of when we do our horizontal steps tells us pretty much that there are m plus k choose m such diagrams. Actually, technically, if we choose m, that's when we choose our vertical steps rather than the horizontal steps. Of course, this is the same as m plus k choose k. And actually, that's the first property that we would like to begin with. So we would like to see that for these Q binomial coefficients, it's true that m plus k choose m is the same as m plus k choose k. And here the idea is that we have to go from an m by k grid to a k by m grid. And there are different ways to do this, but maybe one way to see it is, let's look at a slightly smaller case. So let's look at the 2 by 3 case. This is where we have an example of proving, an instance of proving by example. So if we take this line and we consider the reflection of this with respect to this line, we will get this grid. And now we can see that a path that goes like this translates to a path that goes like this. So actually the partition of the number 5 that we get here, so the partition of the number 5, or actually since we're allowed to have repetitions, it's better to denote partitions, and I should do it back here too. with some sort of brackets. Okay, because when we put the curly brackets, that means set, and in a set we cannot have repetitions. So basically you can see that the partition consisting of 3 and 2 is associated with the partition of just consisting of 1, which will be of the number 1. But the bottom line is that there is a one-to-one correspondence between the paths on the 2x3 grid with the paths on the 3x2 grid using this reflection, and this of course establishes this first property. Okay, so let's move on now to a different property, and actually let's try to understand better a special case. So why don't we look at the case where we have just one row. Okay, so if we have one row, so this is a 1 by n grid, then we can ask how many paths we have, and pretty much what happens here is for each number between 1 and 10, we're going to have exactly one partition that is contained in this grid. So for example, for the number 2, we're going to have this partition that consists just of the number 2. So that means that basically our sum is going to look like 1 plus q squared all the way to q to the n, which makes this equal to 1 minus q to the n plus 1 over 1 minus q. Okay. For our next property, we would like to look at the corresponding property of the Pascal triangle. So let's recall what this property is. So we want to do the analog of n plus 1 choose k is equal to n choose k plus n choose k minus 1. Okay, so that's pretty much the property that establishes the whole Pascal's triangle. And let's see what we have here. So let's look at our grid that has m rows and k columns. Okay, let's do one more row here. And in the case of the usual binomial coefficients, this kind of combinatorial identity comes by considering the combinations that of n plus 1 objects when we choose k of them, and we split them into two kinds of combinations, the ones that contain a specific object and the ones that do not contain a specific object. Actually, the ones that contain a specific object are these ones, because all you need to do is choose your remaining k minus 1 objects from the n remaining objects. And the ones that do not contain the specific objects are the n choose k, because we have subtracted the n and the one object from our considerations. So here we would like to consider let's actually discuss this in terms of paths. So we would like to consider all the paths that go from the lower left corner to the upper right corner and split them into two categories. In the paths that take the first step to be vertical, and in the paths that take the first step to be horizontal. So let's think about how this separate the number for us. So the total number, or rather the Q polynomial that we get. So we're going to have something like this. Imagine first that our first step is vertical. When our first step is vertical, then what really happens here is that we step into this grid, which has n-1 rows and k columns. And so when we reach the upper right corner, it's really like having a path in this grid right here, which means that how many, or what is the Q polynomial that corresponds to these paths? That will be simply m minus 1 plus k and m minus 1 here. Okay. And then let's consider now the paths that start with a horizontal step. So if we take a horizontal step, then now we come up with this grid that has m rows and k minus 1 columns. So I'm almost ready to say that this is m plus k minus 1 with m here. But there is a small problem that when we take a horizontal step, we always leave behind us, or rather define, a full column consisting of m squares. So if we go back to the formula for the partition, we see that the exponent corresponds to the length of the partition. So on the top of the lengths that we consider that are parts of this smaller grid, we have to consider that extra column that has exactly m squares. So we will have an extra m squares that are where each power of q is multiplied by, and that gives us this formula. So you see, exactly because the q binomial coefficients are q polynomials, the formula that corresponds to the usual formula for the binomial coefficients, for the usual binomial coefficients, has also that extra q to the m that corresponds to this column right here. Other than that, you might argue that the analogy is perfect. And these are pretty much all the properties that we would like to discuss for the moment being. Thanks for watching.